Stanford University.
Sorry for the delay. I'm Andy Freeman. Welcome to EE380, first lectures, spring 2009-2010. Since this is the first lecture, we've got some administrative things to finish first. Course requirements are watch and understand all 10 lectures. For each lecture, please submit a brief paragraph demonstrating said understanding via the course webpage, ee380.stanford.edu. You can view lectures both tape delayed and in real time online if you choose. However, there's in almost every case something really cool happens that doesn't make it on the tape or doesn't make it on camera. So your choice. As you may have read from the course description, the topic of this class is computation broadly construed. Why broadly? Because we've got some comments on that in the past. Most schools host talks by successful alumni. I was recently watching one at a not Stanford school by a very successful entrepreneur. And it was an interesting sort of title to the talk and topic of the talk. His talk was basically why I pay Stanford students more than I'm going to pay you. His fellow alums. He said that his fellow alums were just as good, technically, but the Stanford students always brought something extra, an understanding of things outside of the pure technology. And that's what we're trying to do here, is make sure that you have some exposure to things that are not just how do we bias a transistor, how do we design a MOS gate, all those other cool things, how do we do a compiler, but what does it all mean and where does it fit in the world? Today's talk is in that vein. It's a return to an old topic, one of the oldest in computer science, namely, how do we build intelligent machines? Oops. It's a return because we haven't gotten it yet, which is, well, we've only been working on it for, depending on how you count, a little over 2,500 years or a little over 50 years. Part of the problem is that there's a huge mismatch, at least in the last 50 years, between the tools we have and the way we think that brains work. The scales are just all wrong. But another part of the problem is we really don't understand what brains do at some very fundamental questions. Today's talk will address some of those issues and move us a little further down the road. Venkat Rangan is from Qualcomm, and I'm not quite sure why they're doing this. So maybe that will be part of the talk. So thank you very much.
Thanks for coming, everybody. Sorry about the delay. This is an old topic, like you mentioned, and let's see what we can bring new to the table. So this is a small research project within Qualcomm. So there will be a lot more questions that I will ask, then I may be able to answer. It's an old area, so let's see what we can come up with here. So that's the outline of my talk. I'll go into some motivation on why we're doing what we're doing. Look at some biology and the neuroscience aspects. Try to bring some abstraction to the biological details, and conclude by looking at some of the trade-offs and challenges that we're going to face. Sorry. So you might have seen some of these plots before where the text is kind of confusing, but where we look at the computational power of that's constantly increasing. There's this exponential law that's going on. This plot shows you the light blue line is the sum total of all the supercomputers to date, and it's increasing on a nice exponential scale. People have made some fudge factor analysis of how much processing power a human brain has, if that can be quantified, and they've come up with some large numbers. And at some point, it's probably off by a few orders of magnitude, and at some point in the future, people say that, hey, you know what, computers are going to be as powerful as human brains. They say suddenly machines are going to be all intelligent and take over the world. But we still don't understand how even a small network of neurons works. So, I mean, doing that is not the right thing to do. So, and so just to give you some motivations on, looks like so what I want to do is go through some motivation on how good humans are versus brains, versus computers. And what I want you to do is, when you see a knife in this picture, yell knife. So let's see this. Okay, so consider the information I gave you. It's a knife. What does that mean? There's so many different shapes of knives, sizes of knives. There's nothing whatsoever in the information I gave you in relation to what was there. You were still able to figure it out. Those images were moving by at 70 milliseconds with a small gap as a blank frame. In 70 milliseconds, your brain was able to say, hey, that belongs to a category of knife. So that kind of shows you how good we are at processing a concept and taking it down and priming our brain to see an image which we expect to see. It's a very difficult problem in computer science to do that. So this is from Irving Biederman's set of images. So you're welcome to go and take a look at his website. He has some cool stuff there, really cool stuff on. It just goes to show you the difference between where we are with current technology versus where humans or other animals and human brains are. So similarly, you can look at more videos. There's a link on the PDF file. So you did all that by just using neurons that are the basic, that we think are the basic units of your brain. Extremely slow things. These things fire at the rate of 1 hertz. So that's approximately how much time, how much is the time between discrete communication steps between neurons. Maximum output frequency theoretically is 1000 hertz, but they never get there. This is in comparison to the multi-gigahertz processors that we have. We have a very large number of them. That's where the difference lies. It's estimated based on the images that you saw. It's about 5 processing steps if you consider the delays in your brain from the time you saw it till the time you recognize it. Just in 5 stages, you went from a concept all the way down to a real life image. So, and your the number of images you can recognize is extremely large. Just you have that concept, whether it is I say carrot and you hear it, or whether you see it, all of them register into the same idea of what a carrot is. So it's you're generalizing far more. So what can we learn from biology? Computers don't do that well in real life, on real life problems. They're very good at program tasks. They're very good at a lot of things. Computing pi to a million places. No human can ever do that. So there's algorithmic stuff they're very good at. But in real life problems, if something changes, you can program a robot to do a task. If something changes, they may not be able to adapt as easily. So I think that's one area we can learn. We're facing all these semiconductor issues as process technologies scale. Silicon is getting faulty. We have to design architectures and algorithms, more importantly, that are tolerant to faults. You're losing, I'd say, thousands of neurons every day, but you're still who you are, whatever that means. But that doesn't change over time. And so you're operating in a fault-tolerant way. And you're learning rather than being programmed to do every single task, which is quite different from regular computers, which have to be programmed. If you wanted to do something, sure you can do it, but you have to spend a lot of time programming it. Brains are far more general purpose. They tend to learn what's around the environment. They're predicting machines. They predict what is going to happen, and that's the real power. So we think a fundamentally different approach of enabling the machine or the network to figure out what's around it, and then to predict what is going to happen. Give it the right motivations to make it learn, rather than telling it do this. That's probably the right way to do it. That's what biology does. So we talked a little bit about this. Also, we've come quite far in the past decade in computational as well as experimental neuroscience, and we seem to have got a lot more information today than we had even a decade ago. So it seems like a good time to start revisiting the old problems and try to learn more from biology that we have learned. As to what's Qualcomm's take in it, we are good at semiconductors, and so we think we can, based on that, we've teamed up with Brain Corporation, and those guys are building up a strong neuroscience team, and we think that our working together we can come up and help at least answer a few of these issues that I'm going to address in this talk. So I'm an engineer, so I'm not a neuroscientist, and so some of you might not have. Here's what it looks like in at least some labs. I don't have the audio hooked up. But so what you're hearing is spikes from a neuron, and it's typical for neuroscientists to listen to these because they're good at picking out patterns. So people tend to listen to them. This is probably a few neurons that are spiking, and it's a very difficult problem. I'm not trying to say bad things about neuroscience, but it's very difficult to go and figure out a whole system just based on a single probe or even 100 probes. It's as if I gave you a Pentium processor, only this time with 10 to the power 12 transistors, if you will. I gave you 100 probes. I tell you, you can probe any portion and tell me what the software is doing. That's the scale of the problem that we are trying to address. It's not an easy problem. Brains are difficult to probe. So, like the introduction said, we're not the first ones to do it. There's a whole bunch of people doing this kind of neuromorphic engineering, as this field is called. We are a recent entry into this. Is this on? Yes, it's on, but it is okay. So there's a whole bunch of guys. You're welcome to go look at their websites. Lots of really interesting information. Stanford has one, so put that up there. So looking into the biology as well as the neuroscience side, if you look at the top, it's the central nervous system. It's classified into smaller systems, and then there are maps which go into how everything is connected together. Then there's the network level. There are neurons. So descending down the hierarchy, there are neurons, and then neurons talk to each other with synapses. And in each synapse is a whole bunch of molecules that are being used to do the computation. Different companies or different approaches pick different levels of abstraction. We have picked neurons as the basic unit of abstraction. You can go up a little bit, like I think Numenta is a company that does that. They concentrate more on the algorithmic level. We decided that at the neuron level, we don't lose too much while maintaining the right level of detail. So, just to acquaint you guys, here's a little cartoon on what's in a brain. Brains consist of neurons as cells, as its basic units, and each neuron has what are called dendrites and a soma, which is the cell body. And what happens is all these external connections come in. They inject charges into the cell membrane, and all that is summed up in a slightly nonlinear way, and that is passed on to the I'm having trouble with this. That's summed up at the axon hillock. The reason that is very important is, think of it as an analog to digital converter. The analog summation occurs in the dendrites, and that information is, there's almost like a threshold voltage. So if the voltage of the membrane at the axon hillock exceeds a certain value, the neuron fires, and it sends a propagating action potential down the axon, and that is conveyed to the synapses. And at the synapse, a bunch of chemicals get released, and that propagates into the next neuron. If you want to abstract away the axon itself, you can think of it as just a pure delay. And because the signal is preserved throughout the length. Synapses are implicated in memory. They can change the weights, they can change their numbers, they grow and die over time. little babies are born with huge numbers of synapses, and as they learn more and more, they get trimmed down, and so you're born with a huge amount of connectivity. How they're pared down is still a research problem. Each neuron has about anywhere between 1,000 and 10,000 synapses on it, and those are large numbers to go and try to model. Brain also communicates with other parts of the body as well as within itself using neurotransmitters and neuromodulators. For example, learning is mediated by a transmitter called dopamine, and it's attention. So I have to pay attention to something in this room, right? I mean, there's so much happening around. So if I pay attention to a particular thing, there's a different neuromodulator for that. There's all the blood flow that also helps provide oxygen and glucose. We have about an estimate of 10 to the 12 neurons in the human brain. Those are very large numbers. So I don't think we'll get to modeling the entire brain in real time very soon. A reasonable goal is, say, 1 million neurons, which is the size of a cockroach. A cockroach can run around, escape predators, find mates, find food, and it's a very successful animal. Similarly with small mammals, they have, like, a rat has about 15 million neurons in its brain. So we think those are more tractable problems for simulations. So what's there in a neuron? What is the basic thing that causes a neuron to fire? There's a cell membrane which consists of a phospholipid bilayer, and these are extremely insulating type layers. So it's very high resistance. Now, in order to build up a charge across the membrane, there are these little protein molecules called pores or channels, and they're extremely complex, as shown by this little this molecule here is the representation of a real core of a real pore, and the little hole in the center is where the ions can pass through. Extremely specific to the types of ions, like some may be specific to sodium or potassium or calcium, and they don't let in others. Very large numbers of these. And how do pores open and close? How do they decide when something should go in or out? They can be mediated by things like just pressure, for example. So that's how your pain receptors work. So if I pinch my skin, a bunch of these pores are opening up, and that's causing your neurons to respond. They can be mediated by heat or other neurons. So it's electric charge. And there's a typical, so in those little spiking things you saw on the oscilloscope, that's happening because there's some sodium channels open up, they close, and then there's the potassium channels open up, and they close, and finally the internal there are ion pumps that pump all the ions back, so that there's a particular potential maintained across the membrane. That's called the rest potential. It's typically about minus 65 millivolts. So looking at some of the ways to model these things, if you think about it, if you want to model something to this level of detail, and you want to model even 1,000 neurons, that's going to be an impossible task. It's really difficult to do. The Blue Brain project, I think, those guys do that. They have models for each ion channel. They've been able to model about 1,000 neurons or so. That's not very useful. A little worm has 1,000 neurons. So we think we want to abstract it away to some level where it retains as much of its useful properties as possible. So that is a delicate balancing act. So one of the abstractions so neuroscientists are divided into two camps, or at least most of them are. Some of them are believers in what's called the rate code, and others are in spike timing. The rate code guys say that, hey, I don't care about every single spike coming along. I don't care about its exact time. All I care about is there's a whole group of neurons that are firing, and I take an average of them, the average of the spike rate, and that is what is important. There's this other group of neuroscientists that say every single spike is important, and its location and time is important as well. And so we think it's something of a mixture of both. The guys we're working with, Eugene Izikovich, he's come up with this thing called polychronization, where delay is very important in a network. So there's this rather simple animation. So think of a little toy network, 5 neurons, abstracted point neurons. This is very similar to the old neural networks. The only difference is every single one of those lines represents a delay. Also, there's an assumption that if a neuron fires and the signal after reaching the next neuron will cause the next neuron to fire. Very simple assumptions. But if you assume that, you can get a very large number of patterns that are encoded over time. So the way to read these patterns is as follows. There are neuron numbers. The x-axis is time, y-axis is neuron number. So it's 0, 1, 2, 1, 2, 3, 4, 5. So 5 neurons up there. For example, if you take this, is one at what looks like 5, followed by 3, 4, and 1, and so on. So a single neuron, depending on, so this is an animation of the first right there. So 2 followed by 1, 3, and you can keep following that. It's number 2, number 5, and then all 3 of those fire, and then the last one, the 5th one, fires. So it's a very fixed sequence in time. So the belief is that the sequences, rather than just the weights, encode information. For that simple network, there's this very large number of patterns that can stick around. Some of these patterns are cyclic. They're marked up there. Those 2 patterns are cyclic in the sense that they keep reverberating through this network. So imagine that if you have a pattern like that coming along, you have an external input that comes along at some other time. It results in a completely different set of spike timings. So extend that to a network with a few thousand neurons, and quickly you can't even imagine the number of patterns that are there. So these are computationally intractable. You can't really tell how many patterns there are going to be. In fact, in a real simulation, to even figure out what those patterns, what the real patterns are that are repeating is a very difficult problem. So this is one of the approaches we are taking, is assuming that spikes do matter, the spike times do matter. Also, at the same time, rate is probably important. For example, if a command is sent to your muscle, then there's no need to preserve millisecond. So the time scale on that is in the order of milliseconds. There's no need to preserve millisecond type precision when you're moving a muscle. Those are like hundreds of millisecond type events. So at that point, there's probably some kind of rate code involved, but this is something that's still unknown. Any questions or anything that's not clear? So each synapse can change its weight as well. Delays usually don't change. They're based on the length of the axons. Synaptic weight, however, is a different thing. Weights can change. How do they change? There's this old rule called Hebb's rule, the Hebbian rule, and what it says is that neurons that fire together, wire together, and neurons that fire out of sync lose the link. That's a mistake in the PDF file that I sent out. So there's a little mistake there. What it means is that if there's a neuron I'm receiving an impulse from, and it predicts my firing, I will strengthen that synapse. Whereas if there's a neuron that fires after I have fired, it means it's not predicting my firing, and I'll weaken the synapse to it. So it's a very simple sounding rule. It's been found in biology. Lots of experiments have been done that prove there is some kind of rule of this sort that's going on in synapses. This rule has an interesting effect of helping stabilize the network. It prevents epileptic fits in a network, for example. If some neurons start firing a lot, this rule tends to minimize the synaptic weights going to that neuron. So it's a pretty powerful rule considering how simple it is. The rule is called STDP, which is spike timing dependent plasticity. It's a modified version of Hebbian rule, Hebbian learning. Hebbian learning is just anything that's close together will get strengthened, but in this case we say it's not just anything that is close in time, it's something that predicts me will get strengthened. So it's a modified version. So that is a form of what's called long-term plasticity. Plasticity is changing of the synapses. There's also short-term plasticity where there are local chemical changes in the synapses themselves which affect the weight over a very short time scale of maybe a few milliseconds or a few tens of milliseconds. In this picture, for example, the input of the neuron is a bunch of spikes coming in, and that's the output voltage as seen on the synaptic membrane, on the neuronal membrane. A bunch of spikes come in, and the first response is large. The succeeding responses decrease over time. So that's called short-term depression. And similarly, there's the opposite of that, which is short-term potentiation, where spikes come in, and the amplitude of the potential on the receiving membrane actually increases over time. So this is another form of plasticity in synapses. So we have short-term and long-term, depression and potentiation. In addition to that, we have other knobs that we get to play with, which is more stuff in our simulation, which is these neuromodulators. We need a modulator to say, hey, network, you did a good job, so do it again next time. So like the pleasure center in your brain, if you will. So we need some way to modify synapses based on things like dopamine, or say hey, network, pay attention to this input and not to the others. And for that, we need a different kind of knob. So that's, we don't really know as to how these neuromodulators work. What is their exact mechanism of action? We understand some chemical pathways, but these are so complex that it's very difficult to figure out exactly what is happening at the synaptic level. So again, lots of questions. So switching gears to neuron models, there's instead of abstracting away a neuron into a point and saying there's nothing in there except an addition and then it fires a spike, you can think of the membrane as a capacitance and each of the pores acting with a Nernst potential of the ion in series with a conductance that is nonlinear and time varying. So you can say there's like one of those sets for the sodium channel, one for the potassium, one for chlorine, calcium, and you can keep adding more and more as you go along. And the change in potentials are triggered by the various triggers that I mentioned, which is the heat and voltage and stuff. A very simple model, but it seems to pretty accurately reflect what's going on in a neuron. If you run a simulation, if you run a simulation at this and compare it to the real neuron, they agree very closely. So different computational models have been proposed. The simplest is an integrate and fire or a leaky integrate and fire, where it just integrates stuff coming in from this, and this is not really considered to be nonlinear. That doesn't do too well. There's other models. There's one called the simple model, which is a pair of differential equations. That's the one we picked to use. I'll talk more about that. There's the Hodgkins-Huxley model. It's about 5 nonlinear differential equations. So it's computationally extremely expensive if you want to have large numbers of neurons. So we decided not to use that. There's many other types of models. There's a Morris-Likar and there's just different ones. So what is this neuron model? At the top you see a V prime and U prime. Those are the two nonlinear differential equations, coupled nonlinear guys. And there are 4 parameters in them as A, B, C and D. And the amazing thing is that by just changing these 4 parameters between different values, you see that those 2 little yellow squares, they represent a map of the A, B, C and D parameters. By changing that, you can get the spiking behavior of this model to match that of a biological neuron to a very high degree of precision. So very simple computational model seems to abstract away all the ion channels and everything that's going on. This model is being used by a lot of the Synapse project guys, the DARPA Synapse guys as well. I think it can model about 21 or something different kinds of neurons that are found in the human body at least. So what's in a synapse? If you, this is a picture of a synapse, of what a synapse would look like. There's the cell body and a whole bunch of neurons that are kind of sticking onto it. So imagine trying to model something of this sort. It's not an easy task. There's 1,000 neurons, 1,000 synapses, or up to 10,000 synapses for a single neuron. If you say you want to model a million neurons, that's 1 billion synapses. Each synapse will have this STDP rule. It will have maybe the short-term potentiation, depression, as well as delays. So it's just a lot of computation that we need to do, even once you abstract it to this level. Just say it's a weight that changes, rather than saying I'm going to model all the ion channels. So to put any reasonable number on a chip, on a silicon chip, you need these to be submicron dimensions per synapse. Otherwise, you just have no chance of putting enough of these on a chip. Yeah, so there's a lot of work going on. HP has talked about memristors. I think over the past 2 years there's been a lot of news about them. Pretty exciting new technology. There's all kinds of other new technologies that are coming up that have these kinds of densities. How to use them is still not too clear. More conventional technologies have been using floating gates to implement synapses. I think so. Carbomide, he pioneered a lot of this work, and he came up with the sub-threshold operation of MOSFETs as a analog to real biological synapses and neurons. So just there's a lot of detail that I haven't covered really. So I've tried to pack in a lot of information into this talk. So if there's anything that's not clear, do interrupt me. So looking at what are some of the trade-offs, also more of the challenges that we have in such networks. There's a lot of information on this slide, so I apologize for that. We can implement these systems in various kinds of technologies that we know of right now. Silicon is our best bet. We know how to build very large systems with silicon. So if you think about silicon technologies, you can implement these systems with generic PCs or DSPs or GPUs. Those are power hungry, very quick to program up, but probably won't fit in your pocket. On the other hand, if you start using an ASIC or a sub-threshold MOSFET design, those are much smaller. Digital ASICs are also power hungry. Analog VLSI seems promising from that area. So very low in power and extremely small area. The clonability is an interesting column. So how do you take one of these systems once you've trained it and transfer it into a mass producible chip? Let's say I magically came up with this system that learned, and it learned how I speak, for example. It could figure out all my intonations and says it's the perfect speech recognition system for me. How do I transfer it over to a new piece of hardware? Or if somehow this chip learned how to drive a car, then how do you mass produce this thing? So I've called it clonability for lack of a better word. Analog VLSI has trouble in that because there's noise, variations chip to chip, so you can't really clone things very easily. Digital has the advantage there, and yeah. So here's just some cool pictures, really, if you will, on what's been done. There's people who have built synapses with just 2 transistors. This is capable of learning. It implements STDP, but it does it in an interesting way. The waveforms they apply are analog waveforms, and they're the kind of STDP-like, so that the whole response of the circuit is to change its weight based on the inputs. So very clever. At the same time, to generate those waveforms is difficult. So sure, it takes 2 MOSFETs, but how do you generate all that stuff? So there are trade-offs in every way. Here's a picture of the membristors that were fabricated by HP. They've reported on a lot of interesting ways to use them. They seem to be drifting more away from membristors and calling them memristor switches, because they seem to be more like atomic switches. They kind of switch really quickly. So they're having trouble making them switch slowly, which is what we need. So they form good digital memories. They don't form good analog memories, which is what membristors are supposed to be. There's a circuit on top for that was done at Corbina's lab at Stanford, and he's got a whole neuron there. This is going to be our biggest challenge in designing synapses, and we're still working on that. This whole field is called Neuromorphic Engineering, and so it's really interesting and a lot of fun. I have a background as more of a digital guy and some analog stuff, but this whole field has been really interesting, and so encourage you guys to take a look at it and consider that. Some of the challenges that we can think of are some of these questions may not be even valid for such systems. But at the same time, they are applicable to conventional systems that we design today. Let's say you can put this into your phone, for example, and I train it up, and it's really good. I go out and buy a new phone. How do I upload my old pattern into my new phone? That's really not clear at this point. Biology doesn't do it. You can't just take somebody's brain and upload it somewhere else. That just doesn't work. But we may have to do such things simply because of the way we are using these systems. If you take, how do you upgrade? So that's again going back to the previous question. How do you upgrade a system that is built as a learning network right from the start? There's no concept of just plugging in a new piece of hardware and it just becomes faster. You take your motherboard, put a different processor, it runs faster. That's not how these systems work. I don't know if it makes sense to have a bug in such a system. If it's going to be driving your car poorly, what do you do with it? Is there something the algorithm developer can do to fix it, or how do you even implement such a fix? When a memory is sitting in a distributed way, how do you go and just access particular memories and erase them or modify them? If you turn off power to this thing, how much of its learned information is lost. Even if you assume the synapses are non-volatile, there is information stored in the pattern that was propagating at that time. So what does that mean? And how much information is lost at that time? So if you power it back up, what state does it come back in? So these are all open questions. We don't know what's going to happen. We need to develop the usual suite of compilers, debuggers, and all the tools, high-level programming tools to enable other people to use these systems. That's going to be a very big challenge. If we succeed, that's a lot of work for a lot of people. And I think more importantly is, if I give you a chip that is capable of doing this, how do you train it? What's the right environment to train it in? There needs to be grade school for these systems. And how do you evaluate whether a chip has done its job? I mean, how do you prove that a particular design has met its target? Do you just keep asking it questions? Is that good enough? We don't accept that level of testing today. It's a very rigorous test that we have today on qualifying systems that are functional or not. So we need pass and fail metrics for these kinds of systems. And this is just a very short list of the challenges in these kinds of networks. So that I'd like to thank everybody who's contributed to our project, and thanks to everybody who showed up here. Any questions? Yes.
So your last slide mentioned engineering.
If I can get it up.
So my question to you is, what metric are you using for neurons and synapses? Is it just simply the discrete object, or is there going to be an equivalent to something like a bit or a byte or a word?
I didn't understand your question.
Well, what metric are you going to be using for neurons and synapses? It's not like, well, right now we could say a transistor device can represent a single bit of information because of its binary state. But at the same time, a neuron or synapse does not constitute a single bit or byte of information. And I know you left a lot of stuff off, like the velocity of the chemicals that they cross the synapse is only about 200 miles an hour, as opposed to the rest of the electron. If we're going to try to do engineering, the question I think is what metrics are you going to use?
So our take on that is we'll try to stay as close to biology as possible until we find the answer to that. Because we don't know. We don't think it's good to go to the level of detail as the Blue Brain project has gone, which is modeling down to ion channels and all that. It's simply not the tack we've taken. So,
because how do we know that we have the biggest network? It might not actually be the biggest network.
it's an open question.
We didn't learn how birds flew by observing birds. We built planes first.
Yes.
And then so is really mimicking biology, how successful has that been in the past? We didn't build bridges by looking for bridge creatures.
I think we don't have any other way right now. We don't have an Einstein who's come along and told us this is the theory behind this kind of system. So we need to discover, I guess, the principles of lift, the equivalent of it for neurons. And so we're starting with small networks, trying to understand how they work and try to figure out the principles. And if we learn to fly this way, we can decide that we don't need the wings flapping. So that's the approach we're taking. I think computational neuroscience has not reached that stage yet of figuring out what is the theory behind these networks.
So what would a wind tunnel look like then? I mean, that's one thing the Wright brothers had was a wind tunnel, which was sort of an odd thing to do.
We are designing, we're looking at test methodologies for such systems. So that's the equivalent of a wind tunnel. That's where the metrics come in, the pass-fail criteria. And we've just started working on that area.
So the brain may be constructed of neurons, but it's not simply a random collection of neurons. There's a lot of structure and specific ways that these neurons are organized in the brain, which you didn't really talk about. Could you say a few words about the role of the connectivity and structures in the brain and how you plan to accommodate that in your research?
Yes, and like you said, we are trying to imitate biology as much as possible. So connectivity is going to be really important. The different layers, the 6 layers in the cortex, as well as the different pathways that link all the different portions. Those, we are planning to look at those. And those are there for a reason. Otherwise, evolution hopefully would have taken them out. So, yeah, that level of detail I didn't go through in here, but certainly it will be a part of our system.
In terms of neuromorphic systems, where's Qualcomm at right now? What kind of systems are you building? Are you at the stage where you're actually building systems of neurons and synapses and trying to model the first problem you talked about, which is vision, or you're still in the experimental stages?
We're still experimental. There's a new project, so we're just starting off.
Most fields, after they get going, have sort of a typical pattern that's everybody tries to do and do a better job of. It's like, the picture guys have their teapot and the CPU guys have their benchmarks and things. Is this field getting to that stage? Are there any things that everybody tries to do and compete with each other?
I don't know enough about it. I've really been in this field only for a couple of years. So I don't have that kind of level of exposure to answer your question. But at the same time, there seems to be a lot more interest in this area. DARPA is funding at least 2 or 3 large projects that I know of. So I think it's starting to build up.
Thank you.
Thank you.
Actually, the tree structure business, this kid
For more, please visit us at stanford.edu.